Welcome, everyone, to the 49th meeting of New Directions in Group Theory and Triangulated Categories. Today, our speaker is Grigory Garkusha from Swansea University in Wales, and he'll be speaking to us about homological algebra for enriched Grothendieck categories.
Okay, many thanks indeed for the invitation, and I will tell about homological algebra of enriched Grothendieck categories. This is a joint work with my former PhD student, Darren Jones. And I would start with some basic facts from enriched category theory. I recall that a V category, we start with a closed symmetric monoidal category V, and then an enriched V category is consists of the following data. We have a class of objects, and we have V objects of morphisms, such that we have compositions of such V objects here. We also have the units morphism here. All these morphisms are given in our category V. And this data must satisfy the natural associativity and unit axioms. Next, a V functor between two V categories A and B consists of the following data. We send each object in A to an object in B. This is usual, but we take V objects of morphisms in A and send it to the V object in B. And the following diagrams must be commutative. Yeah, so these are enriched counterparts of the usual functors, and nothing special here. And finally, we define V natural transformations between two V functors, namely alpha from F to G. It consists in giving a morphism here. In fact, in the enriched category theory, to give such a morphism, it is the same as to take a morphism, to choose a morphism from FA to GA in V. And the following diagram must be commutative. Again, enriched counterparts of natural transformations in non-enriched setting. Next, what about if we deal with enriched Grothendieck category V? I recall that a Grothendieck category is an abelian category with arbitrary colimits, and direct colimits must be exact, and most importantly, a Grothendieck category must have a collection of generators. So I assume V to be a Grothendieck category and also a closed symmetric monoidal category. We have plenty of examples of such categories, both in algebra and algebraic geometry. And I want to consider the category of enriched functors. I defined, suppose that C is a category enriched in our category V, and consider the category of enriched functors from C to V. What can we tell about this category of enriched functors? It turns out that it is again a Grothendieck category with explicit generators, namely we take representable functors, and this category of enriched functors is also tensor and cotensor over V. Therefore, we can tensor, for example, such objects, such enriched functors with arbitrary objects in V, in particular with generators, GIs. So this is again a Grothendieck category with explicit collection of generators. And basic examples of Grothendieck categories and enriched functors of and enriched Grothendieck category, categories of enriched functors are given by the most naive case is the category of additive functors from B to abelian groups. I recall that where B is say a pre-additive category. I recall that a pre-additive category is nothing but a category enriched over abelian groups. But we have plenty of examples more for a more interesting, like, for example, if we start with the DG category A and we consider DG modules, this is a typical category, a Grothendieck category of enriched functors. In fact, for some problems, I will have to combine serialization in Grothendieck categories with Boosfield localizations in triangulated categories. And in fact, this is the idea behind of all this stuff about enriched Grothendieck categories that I will pass later to derived categories of such Grothendieck categories. And then I will combine both types of localizations. Even though we have a Grothendieck category of enriched functors, it may contain for a genuine homological or homotopical information. For example, like that of DG modules of a DG category, for example. My Grothendieck category can have, for example, a model structure on top of other properties. Yeah, and it turns out that we will use this homological or homotopical information later. And plenty of examples arise in algebraic geometry, where V, in fact, my primary example is when V is the Grothendieck category of Nisnevich or Ital shifts with specific transfers. But such Grothendieck categories don't have projective generators. Let me discuss an example just to illustrate in the naive case when, for example, no enriched information, in fact, when we don't have enriched information, namely the category of enriched functors coincides with the usual category of additive functors from C to Grothendieck category V. So what about for example, if C is the category of finitely presented modules over a commutative ring and V is the category of all R modules, then the category of enriched functors is nothing but the so-called the category of generalized modules. This is an absolutely important Grothendieck category which connects in particular model theory and model theory of modules. And I refer here to Ivo Herzog, Mike Prest, and other people. And it also has plenty of applications in representation theory. So this category is really important and with many applications. And over commutative ring, it turns out that the derived category of the category of generalized modules is compactly generated closed symmetric monoidal. Furthermore, the compact objects are complexes which are bounded complexes of coherence. This category is locally coherent, so it has coherent collection of coherent generators. I wouldn't define, I don't have time to define coherent functors here. What about, so I have told you about closed symmetric monoidal structure of the derived category. And in particular, by the way, this complex, this object regarded as a complex concentrated in 0th degree is the monoidal unit. And this category of generalized models has the so-called Auslander-Gruson-Jensen between coherent objects. In our language, it is given, it turns out that we can define a duality between compact objects, and it is given as usual by sending a complex C to the monoidal units. And furthermore, this category has almost all properties as the so-called almost stable homotopy category in the sense of Hovey-Palmieri-Strickland, except that not all compact objects are strongly dualizable. So this category is closed, symmetric, monoidal, compactly generated with duality on compact objects, but not all compact objects are strongly dualizable. So I have told you about this particular example of the derived category of CR, which is a particular example of a Grothendieck category of enriched functors. What about the general situation? What can we say about the derived category of this Grothendieck category of enriched functors? First of all, when is this derived category compactly generated? In order to apply reasonable boosted localization to it, I would to have the structure of a compactly generated triangulated category. But what shall we assume for this? Well, I start with the derived category of my Grothendieck category V, and I assume that it is compactly generated with a collection of compact objects. And suppose that one of the following properties 1 to 3 is satisfied. Namely, for example, each Pj is K projective, or second, every K injective Y has the property that its value at every object is small is K injective in chain V, for example. Or the third property is, which occurs in most interesting situations, is when the category of chain complexes has a model structure with quasi-isomorphisms being weak equivalencies, and with the property that every injective fibrant complex, in fact, K injectives are such, and has the property that the evaluation of Y at every C is fibrant in chain V. So again, assume that one of these properties is satisfied. Then we can prove the following results. So similarly to Grothendieck category of enriched functors, where we construct explicit collection of generators, we can similarly construct explicit collection of compact generators of the derived category. And it is given by complexes of the form. I take all representables regarded as complexes or concentrated in degree 0, and then multiply with compact generators Qj, where in the situation 1 and 2, Qj equals Pj, or if we are in this situation, then our Qj is cofibrant replacement of the generator Pj. In fact, in practice, Pj is normally cofibrant, but in general, we assume these properties. So again, this theorem tells us that the derived category of the Grothendieck category of enriched functors is reasonably, it is compactly generated it is compactly generated triangulated category, assuming reasonable assumptions 1, 2, and 3 above, or 3 above. Okay, and in practice, chain V has the so-called projective model structure, and the evaluation functor from chain complexes of this category to chain complexes of V is right equivalent. It means that it sends fibrations to fibrations and trivial fibrations to trivial fibrations. Okay, what is next? So we are able in this situation to transfer some homological information from chain V to chain CV. So, but we first need to investigate the category of enriched functors in more detail, because in practice, I take a full V subcategory A in C and can similarly define this Grothendieck category of enriched functors. And what is the relation between these two? It turns out that there is a recollement of the form where CA is localizing subcategory in here, consisting of those enriched functors which with values at A being 0. Yeah, so this functor is the inclusion, this functor is torsion, this functor is the restriction, left, and right come, enriched come. Okay, and I want to then, sorry? We can reformulate the above theorem as follows. I take this Grothendieck category of enriched functors and take the localizing subcategory in it and take its quotient. And then we have these recollements as well. And in particular, that recollement recovers a result of mine and with YM, that this quotient category is naturally equivalent to the category of enriched functors on A. Next, what about the extension of the latter recollements to the derived categories of enriched functors? It turns out that we have the following recollements of triangulated categories. So I start, as I have said, that this derived category is compactly generated under reasonable assumptions, and as well as this derived category. Next, there is this is the restriction functor, yeah, taking a complex in here to a complex in here by restriction. And yeah, this functor is the inclusion from where EA is the full subcategory of those complexes of enriched functors having the following property. If I evaluate the complex Y capital at A and take its homology, then all homology must be 0. Or in other words, the complex YA is acyclic at every A. Yeah, but another property we want to investigate is when we have a localizing subcategory in this in this category of enriched functors. As I told earlier, we will use both types of localizations. Boostfield localization, we combine boostfield localization with Serre localization. So it is not immediately clear to extend these recollements for the situation when I localize the middle category with respect to localizing subcategory Q. And what is the right property to achieve such an extension with respect to CRQ localization? It turns out that the property, the desired property, originates in the categorical interpretation of the celebrated Voevodsky's theorem on homotopy invariant preshifts with transfers. I won't formulate it here, but it has a genuine categorical interpretation in the language of Grothendieck categories and SER subcategories. So, but in our language, the so-called strict Voevodsky property is defined as follows. Consider, so this property is of independent interest in the localizing, in the theory of localizations in Grothendieck categories. Namely, I start with a Grothendieck category D and consider two localizing subcategories Q and S. I say that S satisfies the Voevodsky property with respect to Q if this subcategory, I take all Q localizations of all objects in S. It is not the case that Q localization is again an object in S. No, not at all. Not at all. But if it is the case, then we say that S and Q, the pair S and Q, satisfy the Voevodsky property with respect to Q. In fact, if we start with Grothendieck category of Nisnevich sheaves with transpose, and we take U to be stockwise, the localizing subcategory of stockwise trivial sheaves, and S is the localizing subcategory of homotopy invariants, then Voevodsky's theorem says that the sheafification of a presheaf with transfers is again a presheaf with transfers.
Grigory, I have a
Yes.
Small question.
Yes,
so in the definition of this Voevodsky property, why do we need Grothendieck categories? I mean,
okay, we want to just a second. We want to. I will come to this later, but we will prove the following theorem. There is a recollement of this form, where I take the derived category of this quotient category, and it is not clear that such a category. I start with two localizing subcategories. In fact, I take SA and Q. And if SA, the couple SA and Q satisfy in fact the strict Voevodsky property, then such a recollement exists. We don't know whether it is the case without strict Voevodsky property. Perhaps it is not the case, at least for at least for Grothendieck localized categories. But for the derived categories, it is possible to construct such a recollement. Why do we need such a recollement? I will explain later as an application. Yeah, but again, in practice, I don't deal with any Voevodsky's language, for example, and I want to construct a recollement of the Q localized Grothendieck category. And in general, it is not readily apparent whether it is possible at all. Perhaps it is not. But if we assume the strict Voevodsky property, it is possible.
Yeah, the reason I asked that question was because in the definition of Grothendieck categories, there is this generator criterion. And I was just wondering if the generator fact comes in handy in this step. But anyway, it's all right.
Okay. Anyway, the purpose is to extend recollements above to Q localized. And what properties from S and Q, from the pair S and Q, we require to construct such a recollements? I know, for example, only in the situation when S satisfies the Voevodsky property with respect to Q. And that's it. In fact, it was the Voevodsky theorem which led us to this definition. And as you can see, it is entirely categorical, has nothing to do with any algebraic geometry or Voevodsky theorem. It is abstract. It is an abstract concept which is useful, for example, in our situation for recollements. But another property, by the way, is that I won't tell about the joints of Q and S. Anyway, it has a further remarkable property whenever Q and S satisfy the Voevodsky property, but I won't tell this now about this property now. So I have defined strict Voevodsky's property with respect to Q and S, and now let me pass to its derived counterpart. In fact, Voevodsky's theorem says that over perfect fields, one restriction, Shefification of a homotopy invariant Preshev is strictly homotopy invariant. And what can we translate this theorem into our language? The answer is yes. Namely, I take the quotient category D mod Q, and I take the inclusion functor from the derived category D mod Q into derived category of D. Namely, it takes a complex in D mod Q to its k-injective resolution, and I take an object in this derived category. Okay, k small refers to k-injective resolution functor. But it is important, we take k-injective resolutions in this derived category. Okay, how strict V property is formulated? We say that S satisfies the strict Voevodsky property with respect to Q if, first of all, S satisfies V property with respect to Q, I defined above, and furthermore, this functor k small is such that has the following property. Consider the subcategory EQ consisting of those complexes Z in the quotient category such that the cohomology objects in D mod Q, it is important, not in D mod Q. Cohomology objects in D mod Q of the complex Z must belong to SQ. Okay, and the strict Voevodsky property says that the restriction the functor k small takes this subcategory to the subcategory E, consisting of those complexes in the derived category D. I'm now telling about a subcategory in the derived category of D. Yeah. So such that cohomology of Y belongs to S. It is not the case that in general that such a functor takes such a subcategory EQ to E, not at all. But if it is the case, then we say that S satisfies the strict V property. Okay, So as you can see, this is all these definitions are genuinely categorical, but originate in Voevodsky's theory. Okay, I'm now able to pass to the following theorem. Consider the derived category of this category of enriched functors modulo Q in the middle. On the other hand, I've got the subcategory EQA, which is the full subcategory consisting of chain complexes whose homology belongs to Q localization of S. And this subcategory, this SER localizing subcategory, is the smallest localizing subcategory containing Q and SA in here. In fact, Voevodsky's property, this localizing subcategory is nothing but the join, the so-called join of two SER localizing subcategories. Okay, and in this case, we have such a recollements. Okay, with respect to Q localization. And in the end, I arrive at the following diagram. So I start with the Grothendieck category of enriched functors and its derived category, and then I consider SER localizing subcategory as A corresponding to those enriched functors which are 0 at A. And I've got such a recollements. Okay. Next, above I have constructed a recollement with respect to Q localization. And it turns out that we have a commutative diagram of this. We have plenty of arrows here, plenty of functors, and one recollement can be Q localized, is Q localized to get these recollements whenever we have strict Voevodsky's property. Just to illustrate what we've got, what we have obtained here. Next, consider the category Grothendieck category of Nesnevich sheaves with reasonable transfers. In practice, we have plenty of transfers and finite correspondences, for example, in the sense of Suslin-Voevodsky, and we consider the Grothendieck category of Nesnevich sheaves with such transfers. But C can be another. We can have various reasonable transfers on smooth algebraic varieties over a field K. And Voevodsky defines the so-called triangulated category of motives. In fact, its definition is very simple. It consists of all chain complexes of Nesnevich sheaves with transfers having the property that cohomology sheaves are A1 invariant. Yeah, cohomology sheaves are A1 invariant. A1 invariant refers to SA in our language. Sheaves refers to localizing subcategory Q corresponding to the sheafification. Yeah. Okay. We have the following recollements. We can, in fact, we can fit the above recollements into these recollements. The fact that this functor is explicit, it is the so-called Suslin complex. So the fact that it is left adjoint to the inclusion functor is the celebrated result of Voevodsky. Yeah, and this functor is formal. It's the so-called torsion functor. But what is on the right-hand side? In fact, the left-hand side is well known, nothing new at all. Yeah. But what about the right-hand side of the recollements? Namely, consider the category localizing subcategory in the category of sheaves with transfers consisting of A1 invariant sheaves with transfers. It is a localizing subcategory in this category. And take its derived category. Yeah. So this is a Grothendieck category, therefore I may consider its derived category here. And it turns out that it is part of this recollement, and this functor is given by Q localization. Yeah. And excuse me, not Q localization. This functor is the localization functor corresponding to the subcategory. Sorry. This functor is given by the functor k small above, taking a complex here. Then we replace it by k injective resolution in this derived category and send it into this category in the middle. Yeah. So we have such a recollement. In fact, what is nice is that the derived category here describes explicitly the if I take just a second, let me write something. DM effective of K is in fact boosted localization, boosted localized of D sheaves, the derived category of sheaves with transfers, modular the subcategory, say PA1, denoted PA1, where PA1 is compactly generated, finite compactly generated subcategory of the cones of arrows. Oops, sorry, where is it? Of the cones of arrows corresponding to the projections x cross A1 onto X. Yeah. I take the cones of such arrows, and these are compact objects in the derived category here. So I may apply boosted localization theory to construct such a quotient category. It is equivalent to the Voevodsky's triangulated category of motives. And it turns out this recollement in particular says that the natural functor, there is a natural functor from PA from this compactly generated localizing subcategory PA1 to this derived category, and it turns out that this is nothing but an equivalence of compactly generated triangulated categories. So we have an explicit description as a bonus of this recollement. We have an explicit description of this localizing subcategory in the derived category of sheaves. Okay, and let me stop here, and this is all I was going to tell about. Thank you.
Thank you, Grigory. Can we all unmute ourselves and give the speaker a round of applause? Okay, do we have any questions for the speaker? Well, as we are waiting for, okay, I had another very naive question. So if you go back to this, slide where you had this equivalent form of Serre localization for the first time, so
here.
No, before.
Okay. Okay. What is the question?
Yeah. Here. So like if I like looking at the phrase within quotation marks, so what are these finiteness conditions?
For finiteness conditions, where?
So in practice, you say in practice, these assumptions are typically satisfied when
finiteness conditions. Wait, in practice, these assumptions typically finiteness conditions refer to the so-called weakly finitely generated model structures.
Like
it
generation.
says that domains and codomains of generating cofibrations and trivial cofibrations commute with arbitrary directed collisions.
So some kind of, it looks like a compactness condition, but not exactly.
Compactness, but in the model category theory, we deal with arbitrary colimits, directed colimits, and domains and codomains of trivial cofibrations, and cofibrations are commute with such directed colimits.
Yeah, thank you. Do we have any other questions for Grigory? And can I also ask if you will you be fine with sharing the slides?
Yes, I'll send the slides to you. Yes, no problem at all. Yeah.
Okay, it looks like we don't have any more questions. And sorry, another thing I wanted to ask you. So at the beginning, when we were talking about the papers corresponding to this talk, so I mentioned this paper that is on the archive by you and Darren Jones. You said there is another paper.
Yeah, there is another paper in contemporary mathematics.
Okay.
For example, this result is published there. So first of all, the idea is, we've got this Grothendieck category of enriched functors, and when is derived category compactly generated.
Yeah, it's from 2019, derived categories for
yes, 2019, exactly.
Derived categories for Grothendieck categories of enriched functors.
And then as soon as you've got compactly generated triangulated category here, you may apply boosted localization and then combine hopefully with Q localization if you assume Voevodsky's property. So this is the idea. But first of all, we have to investigate when is it compactly generated.
Are there other situations where this DCV is not compactly generated, but is
I think if chain V is such, then I'm pretty sure that this category.
No, I was going to say when it is not compactly generated, but is well generated, something like that.
Yes, we can further extend to well generatedness, but again, in practice, I deal with model structures with finiteness condition.
Yeah.
Therefore, it is not a well generatedness is not relevant there. It is all it'll give you compact generated immediately.
Yeah.
But we can for example say that whenever chain V is the derived category of V is well generated, then the derived category of enriched functors should be such. Yes.
Okay. I still don't see any questions from people who are not me, but let's thank Grigory again for this wonderful presentation. So the video of this talk will be uploaded to the YouTube channel of this series. We do not have a seminar next week, but we'll be back in a couple of weeks. Okay. Bye-bye.
Okay, my